I do wish I could have a British voice for that. And over to Nick, Mike 0 November Tango Victor. Very warm welcome to you.
Thank you very much. Right. Well, I better just share my screen. Hang on. Let's make sure I've got all the right stuff. I need it. And as I said before, but not everybody was perhaps on. I apologise if this is a bit laggy or anything else, because I'm kind of going through a 4G network here, because we're between broadband. Let's just put it that way at the moment. Right. Okay. Right. Okay. Oh, and yeah. Hang on. No, just a minute. Sorry, I just thought something else that I'm supposed to have done here. Sorry. Now, why is this not working? Stop sharing for a moment, because there's a little button I'm supposed to press here when I'm sharing.
Is that for the audio, is it, by any chance?
Yeah, but also I think I might need to put the sound for the musicians on, otherwise it will filter out some of the, it filters out the background noise, but it also filters out some other stuff that I don't want filtering out. So, right, apologies. You'd think I know what I was doing by now, wouldn't you? I've done it often enough. Right. Marvellous. Great. Well, yeah, lovely to be with you. And yeah, quality not quantity, isn't it, really? But it's and thank you very much indeed, Simon, for inviting me to come and speak. And apologies again, because as I said, yeah, I'm at the AM Society, and I'm going to be talking about building a single sideband radio. But really, what I want to talk about is actually the way I build, which I think actually is helpful, whatever you decide to build. And I know some of you are builders, and I don't know, how long you've been building or what you're. So I'm not going to assume anything. So apologies if some of this is, teaching my proverbial grandma to suck her proverbial eggs. But I always kind of think, well, I'd rather kind of say it all and people think, well, we know this, rather than kind of assume people know a whole load of stuff and they kind of don't. So just a word of introduction about myself. I am a bit of a Johnny-come-lately, really, I guess, to amateur radio. I've been involved for about 5.5 years now, I suppose. I've always been interested in radio and electronics. And when I did finally start going to a radio club and start studying for my exams, one of the things I quickly discovered in this kind of hobby of 1,000 hobbies of ours is a real passion for building my own gear. And it was something that was and still continues to fascinate me. Now, I should say right from the outset, I am not by any means an expert. I am the amateur in amateur radio, right? I have no training in electronics or electrical engineering. I am an ordained minister in the Methodist Church. The NTV in my call sign stands for Nick the Vic, which is what I'm universally known as. I'm just somebody who's fascinated by this stuff, really. And when groups such as yourself are kind enough to indulge me, then I'm always kind of happy to share my passion for building radios. And really what I'm going to talk about tonight, really, as I said, is more about the way that I build, which is important because actually it can make a difficult project doable. And the way that I build, hence the building with blocks thing, is in a modular fashion. It's about taking what could be a complex project and breaking it down into smaller, bite-sized, achievable chunks that can be put together perhaps over an evening or a weekend. And we're going to take a concrete example of something that I built a while ago now, so I've been doing this talk for a while. And you'll see clips of video and lots of photos and all kinds of stuff. There is a PDF version of this slideshow, which I'll make available, and other resources as well, which I'll say more about at the end. But right, let's crack on. What do I mean? Well, when I talk about building, I mean scratch building, so not assembling a kit. Now, let me just say, there is nothing wrong with kits. Kits are great, and as a matter of fact, you know, if you've not done much electronics construction before, then the first thing I would advise is don't worry about any of this stuff I'm about to tell you. Go and buy some kits and build some kits, because that's where you hone your skills. That's where you learn to solder, and you learn to recognize resistors by their color codes, and try and solder your transistors in the right way around. That's always my pet favorite even now. And so it's kind of an important thing to do. So there's nothing wrong with kits, and I still enjoy building kits today. The thing with building a kit, of course, is that in a sense you've kind of got somebody holding your hand, because you generally get, you know, perhaps a PCB, and somebody's picked all the parts for you. You probably get some instructions, and maybe even somebody to call if you can't get it to work. When you're scratch building, you don't really have any of that. You really are starting from scratch. You're sourcing your components, you're designing, producing your own boards. And it may seem daunting at first, but actually it's incredibly liberating as well, because you can do it any way you want, right? Any way you want. And if you change your mind, you can change it and do it. It's your build, right? So it's quite an empowering thing. And the other thing I would say is, in the ham radio homebrew community, which is a little sub-community in itself, are some of the kindest and most generous people I've ever had the fortune to meet, actually. And I regularly correspond with hams all over the globe who are engaged in this same kind of stuff, sharing ideas, and people will send me things. I've had 2 packages in the last month of one guy that had done some boards. He said, "Nick, what do you think of these?" He sent me a load. He says, "You know, I don't want any money for them. Just, you know, build them and see what you think." And there's an awful lot of goodwill, and there's an awful lot of people as well that you can actually say, "Look, I'm struggling with this. I don't quite understand this," or and they will help. And there doesn't seem to be all this kind of one-upmanship of, you know, my radio is better than your radio that you get in some hobbies and walks of life. And there seems to be a genuine kind of spirit of people wanting to help each other get better. And so there is help available on hand when you need it, and we all need it at some point. Now, that was transceiver number 3, I think, that I built. So this actually, I call this the really useful rig, because as you've probably seen, it's built in a really useful box, which is cool, but is rubbish, obviously, for RF shielding, but never mind about that. That's actually a tri-band 804020 direct conversion phasing SDR transceiver, modelled on something that Charlie Morris ZL2CTM built. Now, the only reason I'll show you that is that this is the kind of stuff I do, right? So, you know, when I'm not making videos about stuff, I build transceivers. That's my real passion. We're not going anywhere near anything like that tonight, right? So, and I show people that just because the problem is, you know, when you build something like this and you show this to people, it kind of almost works against me, really, in a certain sense, because people look at it and think, "Oh, that's really cool," or "That must have taken you ages." But then the next thing a lot of people say is, "Oh, I could never do that." Well, that's way beyond where I am. That's, you know, and what I show you that because, you know, it's not all that long ago when I would have been the person saying, "I could never do that. That's way beyond me." But the fact is, I didn't just wake up one morning and decide I could build an SSB transceiver. You know, I built lots of smaller things first and gained confidence and experience, and moved on to bigger things. And actually, what I'm talking about tonight, actually, those are fundamental building blocks not just of the radio, but in your own experience of building, that enable you to go on and build stuff like this or anything else you might want to build. So it's about you know, not running before you can walk. So to build big, think small. To build big, think small. What I mean by that is, it's my contention that it's possible really to think of all analog radio receivers as essentially simply different combinations of the same basic building blocks or modules. And by designing and building in this modular fashion, larger and more complex projects can be broken up into these smaller bite-sized chunks. And there's several advantages to building in this way. The first thing is that you get this sense of satisfaction. If you decided you were going to build a transceiver, and you had one big PCB, and you know, I mean, the chances of it actually working at the end when you put all the parts on are virtually nil, and the chances of being able to fault find where it's going wrong will be hellishly small. So, and actually, a lot of people that have done these huge things, they just give up because they think, oh, it's just hopeless. I'll never know what it is. So, by breaking down a big project into smaller little bite-sized chunks, what you can do is you can build it, you can try it, it may not work, that's fine. So you fix it, you get it working, and then you can test it, and you can tweak it and think, well, it works, but it didn't work quite as well as I want it to work. So you spend some time on it and you get it as you want it. And then when you've done that, you put that aside and you go on to the next module and you spend some time and you get it, you fault find it, you get it working, you test it, you tweak it. Then you pair it with the other module that you built and you get it to play nicely with that, right? And gradually you build it up. But the point about all this is, I mean, it's meant to be fun, right? I mean, this is meant to be a hobby, you know. So if you're not enjoying it, I mean, why just, you know, take up golf or indoor bowls or whatever it is that you're into, you know. So the point is, by breaking it down small, you get some sense of satisfaction that I've done that bit. It may only be one little bit in a big project, but I've done that bit and I feel good about doing that bit. The second thing, as I've already hinted at, much easier to test and to fault trace because you've got less variables going on. If you've got one small section, you can control what's coming in, what's going out, and if it's not, where it's going wrong, far easier. And thirdly, you've just got more flexibility of design. So let's say you build, oh, I don't know, you build a filter. Say you build a bandpass filter. And you build this filter, you get design, you build it, you test it, you think it's all right. But you see a design for another bandpass filter and you think, well, I wonder if that's better than the one I've built. Well, build it. You know, build it and find out. And if it is, swap yours out and put the other one in. And the fact is, if you're building in separate sections, it's a lot easier to do that. If you've got one big board and that's not so easy to do that. But if you can swap things in and out, it's great. Where it's also really good, I haven't put this down here, but it's really good for rapid prototyping. I've got, and perhaps I'll show you later, but I've got a whole drawer full of separate modules of radios that I've built in little tins. And I can throw together a superhet in about 10 minutes. Just because I've got all the different parts that I need, I just wire them up and it's there. So if I want to test a particular thing, like, I don't know, a crystal filter, say, for instance, then I can put that in. I've got the rest of the components there. I can build it around it and test that one bit, and you know, so it makes life a lot easier, and you've got more flexibility in what you actually build. Now, so what are these basic building blocks? Well, I would suggest that there are only really 4 building blocks from which most analog radios can be built, and they are filters, mixers, oscillators, and amplifiers. Now, these are wide generic terms because we all know there's loads of different types of amplifiers. You have RF amplifiers, AF amplifiers, small signal amplifiers, PAs, you know, there's all kinds of different types of mixers. But yeah, broadly, you've got these four types. Now, there is a kind of radio, and this is why I picked this particular design of radio. There is a particular design of radio receiver which you can build, which essentially uses just one of each of these four types, and that is a direct conversion receiver. And that's why I picked it, and that's why I built it, and I use it for this talk. So what is a direct conversion receiver? Well, it goes a bit like this. We've got our antenna, goes into our bandpass filter, and the bandpass filter feeds the signal then into our product detector, which is just a mixer. Just happens to be a mixer that is mixing down to baseband, to audio. And a mixer, of course, 3-port device, 2 inputs, 1 output. So one input is your RF coming in through the bandpass filter. The other input is coming in from your oscillator. And then you will get, as we'll see in a minute, a sum and a difference. We'll pick one of those, and that goes to your audio amplifier and then out to your loudspeaker. So that is it. Now, full disclosure, this is the only bit of RF theory, serious RF theory in the talk. So if this is not your bag, just kind of zone out for the next couple of minutes. But if you're interested in this, and incidentally, I love this stuff, right? This is why I build radios in the first place. The reason I build, because I don't need to, I could just go and buy a radio if I wanted one, right? But the reason I build them is because I want to understand how they work, right? I want to understand. It's not enough to sit in front of a black box and turn a dial. You know, I want to understand how all these things work and why I'm hearing what I'm hearing. So if you're curious, this is how it works. So the direct conversion receiver that I built for this talk works on 80 meters, right? So let's assume we've got an RF signal coming in from the antenna into the product detector on 3697 to 3700. Now, I know you're probably not have a 3 kilohertz wide signal for a single sideband signal, but it just makes the maths a bit easier. So just humour me, right? So let's assume we've got a 3 kilohertz signal coming into the product detector. We're going to mix that with our local oscillator, which is running at 3700 kilohertz. So of course that will give us, well, it'll give us other things as well, but amongst those mixing products, we will get our sum frequencies, which is the RF plus the local oscillator, and that, as you see, will give us a 3 kilohertz signal lying, well, just north of the 40 meter band. And that won't interest us because we'll filter that out anyway, so we can ignore that. What we're interested in is the difference. So the difference is the RF minus the LO. So 3700 minus 3700 is 0, yeah, DC. But hang on, 3697 minus 3700 is minus 3 kilohertz. How on earth can you have minus 3 kilohertz? Some people ask. Well, of course you can't. Well, you can. I mean, mathematically, that's what it is. But in reality, there's no such thing as minus 3 kilohertz. There's just 3 kilohertz. So here's what actually happens. Now, you're probably used to seeing these diagrams. So here's our signal. It's a lower sideband signal lying between 3697 and 3700. And the height of it corresponds to the higher modulated audio signal. So in other words, the highest frequencies of your modulated audio are down at the 3697 end, and the lowest ones. So you can see instantly the characteristic of lower sideband. It's inverted, right? If it was upper sideband, it would be the right way around. So the audio is kind of backwards, if you like, because the signal is inverted. That's fine. That's not a problem to us, because when it comes to mixing it down, what happens is, well, mathematically what happens is that, but in reality, that doesn't happen. What happens is, okay, check this out. It goes 1, 2, 3, whoa, 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 and it folds around the DC point, we say. So it actually lies between 0 and 3. But the interesting thing to note is, you see, that minus 3 kilohertz tells us something really, really important. Now, Bill Meara, N2CQI, and myself have a running, not an argument, but a disagreement about this, really, because he starts, he'll take, you know, the RF plus the LO, he'll take the LO minus, but I always start with the RF for a very important reason, because if you always start with the RF, you will get a negative, and you want to see a negative because that negative tells you that the signal is inverted, which is really, really important to know. So I know when I see minus 3 kilohertz, I know that's an inverted signal, but it was inverted to start with. So we've inverted an inverted signal, so it's now the right way round, okay? So, well, job's a good one, yeah? Happy days. What's the problem? Well, the fly in the ointment is this. Unfortunately for us, 3697 to 3700 kilohertz is not the only band of frequencies that will mix down to 3700 to 37 to 0 to 3. So if we had a signal, an upper sideband signal, between 3700 and 3703, that also, and because upper sideband doesn't invert when it's mixed down, that would also go down onto the same frequency that our lower sideband signal is on. But you say, we ain't got to worry about that. Nobody's operating upper sideband on 80 meters. Well, no, they're not. But what very well they may be doing on a busy contest weekend, you're probably going to get another lower sideband signal, 3 kilohertz above where you are. That's the light green. And the same thing will happen to that. But because it's in the upper sideband slot, it won't get inverted. So this is what will happen. It'll sit right on top of the frequency that you want to listen to. So what you'll in fact hear on a direct conversion receiver, which is why it sounds such a mess sometimes when the band's busy and you think, what the heck's going on here? It's because what you're listening to is you're listening to your properly demodulated audio, but you're also listening to an inverted form of whatever is lying 3 kilohertz above you. So it sounds like, you know, someone's operating upper sideband over the top, you know, of you. So that's why it sounds messy. Now, there's nothing you can do about that. Blame physics. That's just the way it is. The only thing you can do, of course, is to convert your direct conversion receiver into a superhet. And by having an intermediate frequency that you mix your initial RF down to means that you can put it through a narrowband crystal filter, and you can filter out this light green upper bit, so that when it comes to mixing down, you ain't got to worry what's 3 kilohertz above it, because you've filtered it out anyway, so there will be nothing above it, so you can mix it down with confidence. So, and that's why the superhet became so popular, because it overcame that difficulty. But given all of that, it's still a worthwhile thing to have a go at building. And so that's enough of all this faffing around. Let's get building. Now, home brewing wisdom advises that you build backwards, and what I mean by that is you start at the back end of the radio and work your way forward. You don't have to, but you know, let's humour the tradition. So that would be starting with the audio amp, then moving on to the product detector, then the local oscillator, and then the bandpass filter. So here we go. So the audio amplifier. Okay, well. So now, what I've done here, I've tried to keep this as simple as possible. Bear in mind, you know, and I know some of you guys are well experienced in this, but some of the people I'm talking to have really done none of this at all. And so, you know, I'm trying to kind of keep it as simple. Not as simple to understand, of course, the workings of an LM386, but kind of simpler to kind of do in that respect. And this is, I got this design. There's lots of different ways you can do. Some designs with the LM386 sound dreadful, but if you build it carefully, actually you can get some surprisingly good results from that little chip. So essentially, what happens with this is as I put the gain is fixed high, but the volume's controlled by the potentiometer. So you control the volume by limiting the signal going in into the chip. And now, weirdly enough, and this wasn't actually planned, but it's just the way it turned out, all 4 of these stages I'm going to describe I built in a different method. And this first method I'm going to show you is a kind of tried and trusted one, and certainly for digital work and for audio work, which is using a bit of strip board. So that's what we've got. So that's an old 5.1 surround sound speaker, which I was using. And you'll see some more detail in it. So now the great thing about strip board is you can build it small because you can fit things on really good. You cannot, please don't try and use it for RF work. Because I did once. I built an analog VFO. Now everybody told me not to, but I was determined to think, well, how bad can it be, really? And I built this analog VFO on strip board, and effectively I built a scanner, right? Because you could, I could set it going on the bottom of the 40-meter band, go and make a cup of tea, come back. It was at the top of the band because it would because all those little lines you'll see in a minute when I show you, but all those little copper traces act as capacitors, so it's just absolutely terrible. So yeah, drifty as anything. But for audio work, no worries at all, and that's absolutely great. So yeah, so you can fit it all in there. That's a voltage regulator, but I'm not sure if I had that on the schematic there. All these schematics and everything, if you're interested, will be in the PDF that I make available. But yeah, it goes together pretty easy. And yeah, and that's the other side of it. You use, I'm sure you're aware, one of those little kind of bradawl things to break the traces. You do have to be careful, particularly when you're starting out, that because you've got to remember to break the traces. Otherwise, you end up shorting things out. You've got to break them in the right places. You've also got to be careful, particularly when you've got a lot of stuff going on and the solder mounds keep getting higher and higher, that you don't bridge your connections as well, because that's going to spoil your day as well. So there's, but it's not too hard. And as I said, the best thing about it is that you can build it pretty small in terms of the form factor. Right, now I think we've got a little bit of a test that I did on this, so you can hear how it sounds. Okay, well, here is the audio section, and I'm just going to press the play. Now I've got my iPhone here with a bit of Johann Sebastian on there. Turned to about, you can probably just see, about a third of the volume on the phone. So I'm just going to press the play and tweak the volume on the audio app. So, as you can hear, there's a fair bit of gain there and really good sound reproduction there. No hissing, buzzing, clicking, lots of the stuff that you often get with those chips sometimes. If you can build it carefully, then yeah, get some good results. So that is the audio stage. Okay, so that's that. So let's move on now to the product detector. Now I've gone this time again just keeping it simple with an active SA602, 612. They're all the same. NE 602, 612. Little Gilbert cell mixer, which for a direct conversion receiver is quite good, really, because you haven't got an IF section, you've got no gain there, so you end up with using a lot of gain in the audio stage. So actually, to have a little bit of gain in the product detector is no bad thing. This is for 80 meters, so it's fine. If you built this for 40 meters, you could be struggling. Only that I've found, because of that, all those strong AM broadcast stations at the top of the 40-meter band, actually I was getting a lot of AM breakthrough coming through there. So I mean, personally, for myself, I wouldn't use one of these. I've got to be honest. You know, I roll my own homebrew diode ring mixers with audio diplexers and things just to kind of make them a bit more bulletproof. But it works, yeah, and it does work. So, and now they're quite fussy about having 6 volts. So I've got 6-volt regulator there. What have we got? Oh, there's a little choke there just to keep any RF off the power coming in. I think most of this is simple. This is where the audio is coming out, and this is really a little bit of an audio filter which will filter out and short to ground any kind of RF stuff. So that's you remember I said those some frequencies are not going to make it any further through to that, so we'll only get the audio stuff coming out to the audio amplifier. The only thing to really mention is the transformer, and sometimes people get a bit scared about winding toroids and stuff, but I mean, maybe I'm just weird, but I really I really enjoy it, actually. But so this is, and you'll see in a minute, but so this is an FT3743, and so it's just an 11 turns to 2 turns, number 28 enamel copper wire, and because the input impedance of this thing is 1.5 kilo ohms, and of course our RF coming in is 50 ohms, so we need to kind of do something to help match that impedance, and that little transformer will help to do that. Now have we got, oh yes, so I put it in I did put it in a little tin here. I put everything in these little tins. Yes, so that's it. Now, so you'll see a different style here. So this is essentially Manhattan style, but this is I don't know what you call. I call this the Dremel method, really, or the engraving method, and I do this quite often. Sometimes, very often these days, I'll buy those little me pads from the GQRP club. You know, kind of you snap them off, you know, and super glue them on, which are great for Manhattan style. The advantage of those is it's easy to change things because you can flick them off with a standing knife or put them on where you need them. But this can be a useful way if you know what you want to do beforehand. It saves you gluing your fingers together and the rest of it. And that's what I chose to do for this one. Now notice the chip is dead bugged, so it's upside down, and this is the thing that really I used to have to, well, I still have to think about now. But obviously, when we're used to looking at chips, so when we saw the audio amplifier, because we put it onto the board down, we didn't kind of have to think about that, other than when you're turning the board round and seeing it backwards. But you really have to think carefully, because obviously, if you can see my cursor here, this is pin 1. So normally we'd used to pin 1 being here, but because it's upside down, so you kind of have to really kind of remember you're starting there and on the other side. So I tend to kind of draw very often a little diagram of physically what I'm building, not just the schematic, because it's very easy to kind of go wrong. And there's the little transformer there. I used, because it was only a couple of windings on the secondary, I used some thicker wire for that. And yeah, so that was fine. and used a little SMA for the input from the local oscillator. And that's just the power there, the audio jack there, and the RF there. So I think, right, local oscillator. Now, don't be scared here, because I'm going to show you something now, and some people will think, oh, great, and some people will think, what the heck? Right, okay. There's different ways you can do this. For this one, I used a digital oscillator, which essentially uses an Arduino Uno in this case, with an SI5351, which is a phase lock loop signal generator module. Oh, sorry. Which is amazing, absolutely cracking bit of kit, and will produce 3 independent RF signals. So these are great if you're doing a superhet to something, because you can use clock 0 and clock 2, and you know, have the VFO on one, the BFO on the other. A rotary encoder, and a very simple little LCD screen. So you remember that picture, that SDR that I built? So, well, that had TFT screens and all, you know, waterfall displays and all. I'm keeping this as simple as possible. This has got the backpack thing on it, which is great, which means all you've got is the VCC, the ground, the data, and the clock. And for some reason, I don't know why, I always use a yellow clock and an orange data line. So whenever you look at my schematics, I've always got, I don't know why else, but I've just kind of stuck with it. So actually, it's not as bad as you think, because the SI5351, all that's got is the power in, the ground, the clock, and the data. Same for the LCD screen, and pretty much the same for the rotary encoder, except that's got another one, this white one, which is the switch. So that's when you click it in, and what that will do is, in our code, it will change the tuning increment as well. The code, I'll make the code available. I'm not going to go through the code because that'll take forever. But I'll make the code available, and also a couple of the libraries that might be a bit harder to find, I'll make available as well if anybody wants to try it. But it works surprisingly well, and essentially I use pretty much the same code that gets adapted for all my transceivers have this arrangement. Having said that, I don't know if you can see in this tiny box, but I did say before, I did build an analog VFO, this is actually a permeability tuned oscillator on a glue stick, as I said, which is stable enough to decode FT8. So you don't have to go the digital route, but you know, that was what I did on this occasion. The reason I advise people to do this as well is that if you can get confident with this stuff, and if you've never tried it, then this is not the best place to start. You know, then start simple, get an Arduino. There's loads of free resources, play around with it, get an LCD screen, start getting used to text going on it, and get your confidence up, and then when you're ready, you know, have a bash at one of these things. But the fact is, once you're confident in using these things, you can use these things in so many different ways, and it really unlocks a lot of potential. I mean, the SI5351 has been an absolute game changer for home brewers, because to be able to produce stable frequencies that don't drift all over the place, you know, is in something so tiny and cheap is you know, quite a gift, really. So anyway, that's what I'm using as the local oscillator, and here it is. So you can see there we're tuned to 3.7 megs, and actually when you press the rotary, it changes the tuning increment down the bottom. We're tuning in 1 kilohertz increments at the moment, and we've got another building style. I just breadboarded it, yeah, and you can keep it. I make them up. I've got one actually that I use in a tin, so that if I want to throw together a radio or just need a VFO for something, just take it down off the shelf, plug it in, and all this stuff is inside the tin. There's other things you need to do about this. You know, you need to calibrate the SI 5351 and the rest of it. But if you're interested in that, just kind of get in touch. And I've actually got some videos which go into all of the gubbins actually of doing this kind of stuff. And actually, my latest video on YouTube has been to build a far more sophisticated one of these for the radio that I'm building at the moment. But in essence, it's just a step up from what you see before you. But for our purposes here, you know, that's good enough. And with the right libraries and wiring the things in the right way and a fair wind, you stand a fair chance of getting it to work. Right, finally, the bandpass filter. Now this comes from a piece of Windows software called LC, which is a pun on L and C, inductance and capacitance, and it's a bit of software for designing LC filters. And so this actually is a 3-pole Butterworth bandpass filter, and you'll see that stages 1 and 3 are identical. And so now, and if you, I'm sure you're aware, but the 50 ohms resistors on the beginning and the end are not real. The 50 ohms on the end just simulates the load of the 50 ohms you're putting it into, and the 50 ohms on the input is just the 50 ohms characteristic input of the signal. So yeah, now this is what mine actually look like. Now that looks more complicated because I've for some reason I felt the need to put every individual capacitor down there. So that's what I did. I built up these levels of inductance and capacitance like that. There are 3 toroids that you need to wind. So L1 and L2 here and here are 16 turns on a T50-6, and yes, for the a T68-2 is huge, really. But I think it was because I needed 42 turns, and I couldn't get it on anything smaller. So that's why. But I mean, you could put some juice through that thing. I mean, T68. But anyway, but yeah, that's just the way. There are different ways. There's different software. There is some. There's a good web page actually that does identical to this software that you can go and it produce graphs and you can tweak things and see the difference. Well, what happens, you know, if I use slightly more capacitance or slightly less inductance, and you can see the difference it makes, which is really, really useful. You can also do it in things like LT Spice as well. I use that a lot. But that again is a bit more of a learning curve till you've worked out how to use that simulation software, but very, very powerful and free. So that's now what I would say about bandpass filters. I've got one of my videos is called The Dark Art of the Bandpass Filter, because for many years I always thought it was a bit of a dark art, because a low pass filter is pretty simple really, because as long as you follow the design, you build it, you've got a pretty good chance of it working. But a bandpass filter, you know, it's getting it to be the right shape and getting it to be the right shape where you want it to be. It might be peaking too high in the band or too low in the band. So it's good to have some kind of variability. Now, you can, of course, squish the turns together or pull them apart again to vary the inductance a bit. But you'll see I've got trimmers here on both of these end blocks of capacitors and on this series one as well, so I can actually control not only, I mean, this is like a coupling capacitor, so this will enable me to control the shape a bit better, and these will help me to control where the thing is actually kind of sits in the band, which is really, really useful, because depending on what you're doing, whether you want to concentrate on CW or concentrate on sideband or the whole thing, you know, you might want it to sit in a different place. So another tin. So yeah, that's what it looks like. So I think that was a big blob of wax I put in that one there to hold it in place. I sometimes just kind of glue them down, or sometimes I just kind of leave them down there if they're firm enough. I mean, that wire's pretty thick. This is an old one really, because I'm looking at that. I mean, that's the traditional Manhattan style, as you can see, with little pads. I mean, I used to cut these pads up, and I mean, talk about faffy, you know, and glue them down. So I don't do that anymore. I buy the little pads and put them, or I etch them out and use them. But yeah, so works pretty well, as you'll see. So this is the LC model of what it's supposed to look like. And in fact, this is the screen of my Nano VNA. So let me put that one back. So that was the predicted one, and that's what it is. And insertion loss of 0.75 dB. So pretty good, really. And you know, I've had some real good results actually from home bandpass filter. With initial fear of it, because you think, oh, there's so much that could go wrong, and there is. But once you're brave enough to kind of grasp it, actually, it's not too bad. Right. So when you connect these 4 modules together and to an antenna for 80 meters, what do you get? This, and this is what it looks like. As you see, all separate modules. Now you wouldn't have to build it like that. You could build it far more, you know, condensed. You might want to put your modules together on a bigger board or something. That's entirely up to you. You might want to enclose them. In some kind of enclosure. But I was just demonstrating that, you know, this is how it's possible. And in actual fact, most of my transceivers begin life looking like this. They are spread eagled. It's a complete rat's nest of wires and cables and coax, all stuff going over, all these different bits spread out. But amazingly, it works, you know, and I make contacts on it. And actually, the hardest thing is breaking it up and putting it in, shoehorning it into a little enclosure, and then getting it to work again. That's always the hardest thing. So that is it. And I think now we're just going to hear just a couple of minutes of evidence of me actually tuning around. So this is actually what it sounds like on 80 meters. So does it work? Judge for yourself.
Whiskey, Oscar November 7, Foxtrot Lima. Golf Yankee Whiskey, this is Oscar November 7, Foxtrot Lima. WX here in Belgium. Yes, we had in the weekend we had some little snow during the evening, but all the snow has melted. This morning also a little bit snow, but that was nothing at all. And yes, it's cold outside. It's cold outside. The temperature is okay. Das merkt man schon. 520 Mantel, oder?
So that's it. Thank you very much for listening. Just to say, there is a PDF version of this presentation plus the Arduino sketch and libraries all available to download at the top of my qrz.com page. If you just put in M0NTV into QRZ and you'll see there's a building with blocks section, and there's a link there to download those. And if you're interested in any more of my kind of home brewing exploits, then you can follow me on my YouTube channel. Just search on YouTube for M0NTV home brewing, or just put M0NTV into Google and my YouTube channel will come up. Thank you very much, and thanks for the opportunity of talking to you. And if anybody's got any questions or comments, then yeah, be glad to talk to you. But thank you.